So guys, welcome back. Today we continue with Fourier transforms, discrete and continuous Fourier transforms. So first of all, the outline of the presentation, I'll talk about Fourier transforms, DFT, discrete Fourier transforms, orthogonality, and Fourier matrix F, and DFT matrix. So what about classical transforms? Some of us need some, let's say, a little bit kind of a review. In fact, classical Fourier transforms apply to functions. So, but discrete Fourier transforms, or what you call generally DFT, apply to vectors. So for real Fourier series, we have what we call real periodic functions, where f of x plus 2 pi equals f of x. Of course, you know many functions like this. And in general, complex Fourier series are complex periodic functions. Fourier integral transforms, they talk about complex functions, f of x for x, which is in the set of real numbers between minus infinity and plus infinity. And discrete Fourier series, they talk about complex vectors, f. We see f here is f0, f1 till fn minus 1. And now our focus is on the last one. The last one, which transforms vectors to vectors. Okay? So that is achieved, in fact, using what we call n by n matrices. And the inverse process uses what you call the inverse matrix, or the inverse Fourier matrix. So the first thing we have to learn is what are the basis functions we need. So all these transforms, in fact, share basic or basis functions of the same type as the Fourier which is used. So for real Fourier series, we use cosines and sines. So cosine nx and sine nx. Okay? And for complex Fourier series, we use what we call complex exponentials, like e to the power I n x. For n, which is a relative integer number, so it's 0 plus or minus 1 plus or minus 2. Okay? For Fourier integral transforms, we talk about complex exponentials, e to the power ikx, where k is between minus infinity and plus infinity. And for discrete Fourier series, we talk about n basis vectors, bk, with bkj, which is equal to 2 pi e to the power 2 pi ijk divided by n. Or what you can also write as e to the power 2 pi I to the power n over n all to the power j. And you see here immediately there is a relation where you can say that the discretization comes from the fact that you are substituting x by kind of something like I to the over n. Okay? Like we usually do in calculus 2, when we split the interval into n subintervals. So each function and each vector is expressed, in fact, as a combination of Fourier basis functions. So these are the basis functions, in fact, we usually use. The cosines, the sines, the complex exponentials, okay, e to the power nx or e to the power nx. And in the case of discretization, you replace the continuous variable k or x by what we call I over n. So what is exactly the transform? This transform, in fact, is the rule that connects a function or the vector to its coefficients ak, bk, ck, f of k, and these combinations of basis functions. So for real series, the combinations, they may allow you to write f of x as a combination of the sine and cosine, see, with different angles. You see the only change here is with the angle. So you see a0 plus a1 cosine x plus b1 sine x, and you see the a's here, they go with the cosines, and the b's, they go with the sines. Okay? And it's easy to write it as just in a compact form as the summation. Got it, guys? And for the complex series, if you are writing your function as a complex series, like we did at the end of math 1 and 2, you can write it using e to the power ix. The only change here is with the number you're going to put in front of ix and the exponential. So your aim would be to find this coefficient, the C coefficient, C0, C1, C, C minus 1, C2, C minus 2. And here you will see that there is a correspondence between the number, which is the index of the coefficient, and the kind of the coefficient which appears in the complex exponential. For the Fourier integrals, in fact, we may define them as f of x, which is equal to the integral from minus infinity to plus infinity of this function, which is called, we call it the Fourier function, f hat of k, e to the power ikx, and the integration here is with respect to k. So k goes from minus infinity to infinity. So f of x is the integral from minus infinity to infinity with respect to k of f hat of k times e to the power ikx. And for discrete series, the discrete case of this, you will be writing f as c0 b0 plus c1 b1 plus cn minus 1 bn minus 1, using what we call, or as a Fourier matrix f times c, if you wish. So, in fact, what are we talking about here? Some of you may say, oh, what are we talking about? In fact, the Fourier transform would take f in the x space to its coefficient in the frequency space. And the goal, of course, is to kind of to study the thing you are dealing with, whether it's a function, whether it's a vector. So, but the inverse transform starts with the coefficients and tries to reconstruct the original function. So there are two main steps here we can declare. First of all, computing the coefficient is what we call the analysis step. And with MATLAB, we use the FFT syntax. And reconstructing the original f is called the synthesis, and we use IFFT with MATLAB. Okay? So orthogonality, in fact, there is a property of orthogonality. In fact, the transforms have nice formulas in general, because the basis functions are orthogonal. So often, the basis contains eigenvectors of symmetric operators. And we can find each number ck in the, for example, in the previous discrete series, each number ck could be found separately. So for vectors, we just take the complex dot product, bkf, between f and each of the orthogonal basis vectors bk. So we may write bkf as bk c0 b0 plus bn b1 c1 b1 till cn minus 1 bn minus 1. So this is, in fact, this is just f, okay? And we can write it as the dot product ck bar times bk. So in fact, you could write ck itself as bkf divided by bk. So all inner products, in fact, bk bi, are 0 in this equation, except the one which that you may say it appears in the diagonal, bk. And those denominators, in fact, are easy. They are either equal to pi, 2 pi, or n. And they are generally a pleasure to compute for Fourier basis functions. Okay? So the series we can obtain kind of cosine nx squared integrals, and they usually give pi. Similarly for sine of nx squared, and they usually give pi, or just the integral of n1 squared, which usually gives 2 pi. And this is in the case of the real series. For the complex series, if you are integrating e to the power ikx times e to the power minus ix, we usually also get just to integrate 1 over the period, which is 2 pi, and we get 2 pi. For discrete series, we're talking about this complex dot product. We multiply the conjugate of b by bk, and you can see that you are adding n times 1. So 1 is just 1. Here, this is again e to the power 0. Here, this is again e to the power 0. Okay. So if we normalize basis vectors to bk equals 1, norm of bk or magnitude of bk equals 1, then Fourier matrices are in fact orthogonal. And this is what we will show later on. So the Fourier integral case is the subtle one, and we stop after writing down equation 2. This is equation 2, guys. Okay. So its infinite integrals come from Fourier series when the period 2 pi increases to 2 pi t, where t goes to infinity. So in fact, when you write f hat k, here I added, there is f hat k, of the Fourier functions here, okay, which is the integral as we did, as we defined before, from minus infinity to infinity of f of x e to the power minus k, e to the power minus I k x, here should be k, and f of x is 1 over 2 pi, the integral from minus infinity to infinity of f to the power hat, f hat, sorry, of k e to the power I k x dk. Then there is a correspondence. So the Fourier integral case is the subtle one, was just defined by this continuous case. Okay. So now we talk about the things we're going to use. The Fourier matrix F and the DFT or discrete Fourier matrix gamma omega. First of all, the matrices Fn and omega n are n by n matrices. They are both symmetric but complex, and they do have the same columns, but the order of the columns is different. In fact, what about the components of Fn? First of all, Fn contains powers of W, which is e to the power 2 pi I to the over n. Remember, we said that like this is the kind of discretization where x is substituted by 1 over n. And omega n contains powers of the complex conjugate, which is W bar, which is here should have been let's say omega in complex. I should have used another complex, which is equals another mathematical symbol, which is e to the power minus 2 pi I over n. Okay, so these two guys are the conjugates one of the other. This is a mistake, guys. So this is the conjugate of one of the other. In fact, the two matrices are complex conjugates. So you can say that the conjugate of Fn of the Fourier matrix is the omega matrix, the discrete Fourier matrix. And here are, in this example, F4 and omega 4, containing both of them powers of W, which is equal to e to the power 2 pi I over 4, which in fact should give you I, and the conjugate, which is e to the power minus 2 pi I over 4 here, and this should give you minus I, another type here. So these are the two matrices, for example, in dimension 4. So you start counting the rows here from 0, 1, 2, 3, okay? And you see that F4, and this is its conjugate, which is the FT matrix, omega 4, okay? So, in fact, there are a couple of remarks, is that in general, omega times F, the vector, produces the discrete Fourier coefficients we're looking for, okay? So the inverse F times C brings back the vector, which is NF. So in this case, in the case of dimension 4, we'll get 4F, okay? Because F times omega is NY. The two matrices are orthogonal. So if you multiply Fn by omega n, you discover a fundamental identity for discrete Fourier transform. It reveals the inverse transform, which is given by Fn omega n, which is equal to ny. This is the identity, huh? And therefore, you can say that the inverse of the Fourier matrix is equal to 1 over n omega n. So, in fact, you could replace omega n by its conjugate form, which is Fn conjugate. So, in fact, because f n itself is a complex matrix, you see that f n inverse is 1 over n f n conjugate. The n numbers, in fact, we obtain here are equally spaced, and the n has an impact on how to place them. They are equally spaced around about the unit circle in the complex plane. Okay, so there are n solutions in the nth degree equation. What I mean by they're equally spaced here, guys, I mean the following. Let me draw the figure. I mean, we have this case. We have this kind of beautiful shape. This is the unit circle in the complex space. Okay, and I'll be here taking the same size we had in the previous slide. I'll put these W's. Okay, so this is W1. Okay. Okay. I'll take 8. Okay. So I'll take W3. Here I get W5, and here W7. Okay. So from where one could ask, from where these come from? Here we said that in the formula that these are given by, in fact, W is equal to e to the power 2 pi I over n. Okay, so if you start with 1, how much you get is e to the power for n equals 4. For n equals 8, sorry, you get 2 pi over 8, so it's just I times pi over 4. So you see the angle here is 5 over 4. Correct? Okay. Now, the next one would be placed here. This is W2. Okay, equally spaced. So you have an angle pi over 4. The next one, W to the power 3, will give you 3 pi over 4. The next one will give you just W to the power 4, which is again equally spaced from the previous one, another pi over 4. And you see this way, they are equally spaced, as you see on the unit circle in the complex plane. Okay, so these numbers you got are equally spaced around the unit circle in the complex plane. Moreover, they are all solution to this equation, z to the power n equals 1. And moreover, if you sum them up, you get 0. And this is very specific to the fact that we are dealing here with complex. And the proof of that is to multiply just s by w again, and you can see that it will, because z to the power n is equal to 1. This would produce again w plus w squared till w to the power n. Okay, so this is the last slide, which shows an example on how the discrete transform Fourier transform works. So you start with any n-dimensional vector. Let's say this is the main dish, and we'll continue with this inshallah next time. So you start with any n-dimensional vector f, okay, which has components f0 till fn minus 1, and you see here we are starting from 0, so we have n-dimensional component. So the discrete Fourier transform, in fact, what it does, it expresses f from a vector as a combination of what we call the Fourier basis vectors. The Fourier basis vectors are these, and it uses the coefficients it found, C1, C0, C1 till Cn minus 1. Okay? In fact, those basis vectors are the columns B in the Fourier matrix. Okay? So you use the basis you have in the Fourier matrix, to write down f, this guy is f. It is written now as the product of b0 till bn-1 by c0 till cn-1. Therefore, one can write the following. You could write that f, in fact, is the Fourier matrix of size n multiplied by c. And to find back c, so your goal is to determine these coefficients. It's fn inverse times f. So, in fact, as you've seen from the previous slide, c, its f inverse is 1 over n omega n. So you need the discrete Fourier matrix here to find the c's. So what happened here, you just wrote this n-dimensional vector as what? As a combination of the Fourier Basel vector by the coefficients you just were able to find. The forward transform, so this is what we call the forward transform. It transforms C and multiplies F by the DFT. Okay, so we just multiplied F by the DFT, get the C's. So this is what we call the Fourier transform, and this is what we call, in fact, the analysis step. So what happened here when you multiplied, you separated F, which was a vector, into n orthogonal pieces. What are the orthogonal pieces? The components of the basis, of course. You got it? And because we did a lot of linear algebra before, you understand what we are talking about. In fact, this is what we call the analysis step. So inshallah, we'll come back to it next time and continue to see more about discrete Fourier transforms and stuff like this, and a couple of course, numerical examples.